asked to use the mic. So.
Yeah. Oh, yeah.
Kia ora tātou. I think we'll keep moving with this session. We're hearing about some really great studies here today. So I've got with me now Alan, so I'll leave it up to Alan to tell you about his interesting research. Thanks,
Thank
Alan.
you. Kia ora, good morning, everyone. I'm Alan. I'm from Auckland Bioengineering Institute, University of Auckland. I'm here today to talk to you about SPARC and what it is, how we get here. And thanks so much for coming to my talk, and thanks so much for this opportunity for me to be here. So first things first, what is SPARC? So SPARC is an NIH funding program from the US. SPARC stands for Stimulating Peripheral Activity to Relieve Conditions. It's an open science initiative to advancing understanding of the autonomic and peripheral nervous system. It provides researchers with a collaborative, fair platform to drive discovery and innovation. Over the years, it has funded many different teams in the US and overseas, in Europe and in New Zealand, to map the nerve organ connections. I think there are probably 70-something teams that they have funded. And here in Auckland, the Auckland Bioengineering Institute, what we are responsible for is to build an interactive interface, modular continually updated visualization of nerve organ anatomy and functions. So we have a lot of data, and we need to transform them into something that we can present on the web. So that's what we have done at the ABI. So to do that, right, we have this SPARC portal, SPARC.science. It provides a unified interface to the SPARC repository tools and services. And the data is stored as data set. It can be shared. They are all open for anyone to download as well. There are, at this moment, when I checked this morning, there are about 411 public data sets are available. And it hosts multi-species and multi-model data sets, as I mentioned, and data including images, segmentation, simulation models, anatomical scaffolds, so these are 3D models. And some of them are even open source device designs as well, which is very interesting. And another thing that we have done, right, is to provide web-based visualization of all of the anatomical and functional maps. So those are the 2D maps, 3D scaffolds, so these are organ scaffolds or whole body scaffold, well, simulation, as I mentioned. And this portal is maintained and developed by teams across the globe. So there's a team in Switzerland, team in UCSD, and in Pennsylvania, and here in Auckland as well. So you can imagine organizing a meeting with them is quite difficult. Everyone wants to have their sleep. So a bit of background before I jump into the portal of what we have done at the ABI. So software development began very early, before 2001, even before ABI was founded, when the core ABI group was still part of the engineering science. And majority of the software developed by us are open source. We encourage people to share our codes, and so that everyone can use them or contribute to them. So some of the major software projects that we have created or worked on previously, including CMNIPS. So CM stands for Continuum Mechanics. We use that to solve 3D mechanical problem on our organs, and also many other things, including electrical activity of our organs. So in this one is a screenshot of a CM GUI. It's some very early day software that we created back in the 2000s. Here, what you see is a heart model. What interesting about this is on the background, what we have done is simulate with electrical activity, so simulate that, and then which will activate the muscle fibers, and then it causes the heart to deform. So it's simulating the heartbeat from a very basic level. And then other software, including CellML and OpenCore. So CellML is an XML-based markup language representing mathematical models. In this case, particularly used for biological response and physiological problems as well. And OpenCore is used to solve, you can use OpenCore to view, to edit, to simulate, and to analyze the CellML model. And then we have PMR2. So from the previous talk, you may have heard of visual model repository. So we use that. So PMR2 is the framework to host and to monitor, basically the framework for you to look at what is in the visual model repository. So in general, so its version control is similar to GitHub, but with a major focus on the cellular model, so that the researchers can easily find them, because they are all very well annotated. So why did I say that? Because that is the background and the capability we have, and that helps us to achieve what we have done for SPARC. So first things, what we have done, we created these flat maps, so they are like 2D map of the human body or any species, including rat or pig as well. So they are like Google map, but not of the street or cities, but instead it's the human body or any species, really, that we have worked on. And 3D scaffolds, these are all customizable 3D models of generic organs model of the human body, based on the knowledge that we have built up from creating CMNIPs. And we also created web-based 2D flat map and 3D model viewer, so that the user can just go into the web, they find something interesting, and then they can take a look at them right away without having to download them. And then what we have done is also a web-based open core, so if you are interested in a certain simulation, you can just run them on the web without having to download them. And we have also created UIs so that to make data discovery simple. And then we combine everything together to make a single integrated viewer so that you don't have to go to different tabs on the browser to open them up. In one single viewer, you have the 2D, 3D simulation, images, and everything. Yep, so a little bit more information on how we created the flat maps. So we have biologists handcraft the S3G diagram of different organs, put them together. But then what we have also done is work with the team in UCSD. They take a look at the neural connectivity and population. They analyze them, they run it through NLP algorithms, and then curate them. So there are a lot of them qualified curators to do all this hard work for us. And then we combine them together using Flat Map Maker. It combines the 2D visualization with the connectivity information, put them together, we upload them to the server, and then we can access them using the 2D viewer. And then from there, we can also inquire the server for if I'm interested in certain connectivity, neural connectivity. I can find all the relevant information of it. So you can see a little screenshot of a wet there. It's very small, and then we have the 3D scaffolds from Scaffold Maker. What you see here is actually a very generic model of our uterus. We have many different scaffolds as well, like including stomach, intestines, heart. But what makes this very interesting is they are very highly configurable. You can change the perimeters, you can change the length of the tubes, you can change the thickness, you can change the wall thickness as well. And then you can change the angle that you bend. So it helps you, it gives researcher a tool to create very generic organs models based on the species, because organs for different species look very different. So this tool allows us to have a quick way to make a very generic models. So if there are data from images in the future, right, we can easily fit them based on the very generic models that we have here. And all this configuration for the 2D map and the 3D scaffolds, they are uploaded to PMR2, so other people can download them, run through the workflows, and then they will get the exact same result. So one focus for us is to make sure everything is reproducible, and that's what we are trying to do. And after we have done all this, right, we export them into a format that we can read on the web. So finally, the portal. So here is the front page. Don't mind the little banner there. All NIH website require that little banner saying that it's under review. But on the homepage, you can find a whole lot of information. I can't scroll down from here because it's a screenshot, but it basically highlights all the things that we have done. And then we have a farm data page. So these are the pages that you will find most of our data sets. So it has, you can do a keyword search or you can use filters. So filters including species, anatomical structure, age, sex, and where they are funded from. Once you find a data set that you're interested in, you can go into the data set page. And here is a whole lot of information that you can find, discover for a certain data set. In this one, so this one is about the levels in a human inferior hydrogestic places. But what you can do is you can go to the Files tab, you can look at what files they have, you can go to Gallery to see what sort of visualization they have as well. And you can cite all this because there's DOI. And more importantly, all this can be downloaded for free. Well, except for the data transfer cost, of course, but they are all openly available for anyone to access. And then this is the integrated viewer that I was talking about. So these are the 2D maps of the human. You can see that it has the organs, all the organs there, and then we separate the spine so that you can see how the neural connectivity, how it connected from the spine to different organs. So each of these are clickable. You click on them and then you will pop up a little information box on the side that you can, if you are interested in, you can go and look for even more information. And you can see that there are markers all over the place. So these are the data set available for that particular anatomical region. And the number there show you the number of data sets that is corresponding to that organs. And then here is a mini version of the Find Data page. This is a sidebar that I was talking, the UI that I was talking about. It has the same capability. You can use a keyword search. You can use a filter to find information. So this one particularly highlights things that you can view using this viewer. So yeah, more example of the, so I use a filter here that says scaffold, and you can find all the data set that has 3D scaffolds. At the top there, you see there is a vagus nerve 3D scaffold. So these are not a generic data, actually. It's an actual vagus nerve from images. So what we have done here, well, because it's a very long segment, so the micro-CD team, they have to chop it up, and then we have to stitch them all back together thanks to the magic of the mapping team, of the scaffold team. We are able to do that. And then bottom is a generic scaffold, but this is just to show you that we also have the capability to display multiple viewers at the same time. I think we can display up to 6 of them. If your screen is large enough, then that's great. If not, better don't go with 6. And then here is another scaffold that we have. It's a 3D whole body scaffold. So it's similar to the 2D scaffold. There's a lot of detail to it. So all the organs that you see there are the generic scaffolds that we have created, and then we put them all inside. There's some problem with some of the fitting. You can see the muscle popping up of the skin. Never mind that. I don't think that person is very comfortable though. And then one more thing, I was talking about the neural connectivity information. So if you click on any of the nerve, it will pop up this little information box on the sidebar. It will tell you where the nerves come, where it goes, where it passes through, and then also a whole lot of citation underneath. What you can do is you can hover each of these names, and then it will show you the exact location. And in this case, right, the top is the 3D scaffold, and then you highlight the nerve of this particular selection, and then at the bottom is the 2D map, flat map, showing you where this nerve connected to and from as well. And then finally, I have this, well, here is a functional map. It's another type of 2D map that we have created. We present blood volume control diagram here. So it has a lot of different chemical channels. So some of the data set may contain this sort of information. And then on the right-hand side, you can see that there's a simulation viewer online. You can change all these parameters, and then you update the diagram, update all the plots as you go. So we don't have that many data sets about simulation yet, but in the future, we would like to increase the interactions between them and then have more of them for people to use. So not much time for me to go over this, but these are all the codes. All these are available on GitHub. they're all individually packaged modules that you can, if you are interested in a particular field, you can just download that. You can check out the codes and use them and deploy it somewhere else. And not much time for future development, but what we are focusing on now is we have done the visualization part quite well now, so we are just looking into fitting more customized data into them. And hopefully, this framework is easier enough for other people to use as well, so we are looking forward to working with other groups of people that we can put these interactive viewers to other places and used by other research as well. So that is something that we are trying to work on. And then thank you so much for this wonderful team of people. So we are led by Peter Hunter and co-PI David Liggins and managed by Dana. So this wonderful team of people make sure everything that can happen happens. And finally, thank you so much for your attention, and thank you so much for listening to me. And here is just some photos that I took in 2024 at Minnesota. Thank you so much for ABI and really NIH for the opportunity for me and the team to go overseas, to go to US, and to bring Kiwi's technology to them. It's really wonderful and privilege for me to go there and show what Kiwis can do. Yeah. So thank you very much. Thank you.
Kia ora. Thank you, Alan. Have we got some questions for Alan? Chris?
When you start to learn surgery, you start to realise that there's all these variations and structures that the textbooks say are always the same way. Can you build in some of the common variations into the models?
Yeah, so we are looking into that, right? Even for nerves, there can be a lot of different variation. Not just we are looking in, so I'm not quite sure where we're heading to at this moment, but it's always in our mind that we want to show some of these variations, especially in nerves, right? Sometimes we want to see the variations between species as well. So it's that sort of things that we want to highlight in the future. And if we have more, maybe funding from NIH, hopefully, fingers crossed, then we will be able to do these sort of things. But yeah, it's always in our mind that we need to be able to represent the variations better. Yeah.
I have a question about the portal, which very neat, by the way.
Thank you. Yep.
Had a look at data sets. You mentioned that all data is open, but who supports the cost of the data transfer? Because on the when you showed there was I think 1 point something terabyte of data.
Yes, and there's a lot of images, and there are a lot of, so I think NIH has this open data initiative, so that's what they are doing. Although I think some of this funding has been cut now since you know what happened. But I think it's always in NIH mind that they want all this data to be open.
So
And
if you go to the website, you can download that.
well, not, so for really large data, you really need to have an AWS account because the storage is free, right? But they don't want to cover the cost of the transferring the data, so you have to pay for that part yourself.
Thank you.
Thank you, Alan.
Great,
I think we'll
thank
move
you.
on now. Please find Alan at lunchtime if you want to chat more.
Finally, you want to look at it in action. Is that solution?
Which one are you?
Jeff, investigating that stream, the second one.
Jeff, I'll just I'll hold up that when you're at 15 minutes.
Yep.
So you have 5-minute question time.
Yeah, cool.
Yeah.
Excellent.
Kia ora. Our next speaker is Geoffrey. I'll let you speak to your
thank
own
you.
work.
Kia ora everybody, called Geoffrey Toku Ingoa. I won't sing my favourite song. It would be Elvis Presley, The Suspicious Minds. But I'll save you the trouble of having your eardrums blasted out. So I thought I'd talk a little bit about what we do at REANNZ, at Mahuika Support, and in particular I was going to talk about extreme performance variation that we found when running some chemistry code. As classic as it is, I changed my presentation title at the last minute, but it's still in line with what's going on. So just an overview of what REANNZ is. I think everybody sort of knows what REANNZ is. We host sort of networking facilities, but in particular my part is the HPC, is an HPC role. So I'm a research support specialist at REANNZ, and I look after Mahuika, which is our HPC. And we have on Mahuika about 100 nodes that have 100,000 plus cores running on it, with terabytes and terabytes of RAM as well running. So we have quite a lot of computing that's going on. And in particular, being at Mahuika support, I sort of think of myself as a gopher for all of the computational problems that we have left, right and centre. So we're here to provide help with what problems and issues that that users have with research support, with research software on the platform. And this can be from just getting set up on the cluster to research domain-specific software help. My background is computational chemistry, so in particular I look at things from a chemistry point of view. If you want to find us, unfortunately it's a little bit confusing at the moment since our docs page is still docs at NESI, or docs.nesi.org.nz. We're trying to cut out the NESI. But if you Google Mahuika support or REANNZ support, you'll find us and click that button there. And we want to hear about any problems that you've got running on the platform. We've got lots of ways that you can contact us, as I showed before with the web page. We've got our office hours, but we've also got education and training. In particular, a lot of the work that's done by Nisha at the back. Where it comes to upcoming tutorials on our training calendar, where we have all the webinars and tutorials that you can find that we showcase, as well as webinars and tutorials on our YouTube site. So today I thought I'd talk a little bit about some of the how complex it can be to look at investigating problems on the HPC, in particular looking at a chemistry case that I've been working on, and sort of show the steps behind what it takes to solve difficult problems on the platform, sort of giving you guys a look behind the curtains of what we do at NESI support. In particular, I just want to emphasise and showcase the level of support that we provide when we encounter challenging problems. So this is the only case study, I don't know why I put case study 1, but case study only, which is major degradation in GROMACS, which is a chemistry software which is designed for doing molecular dynamics in chemistry. And we had a user that came to us and said that they were having a few problems because what you can see is that they started a job on the 14th of December, and in one case it was coming out as being finished in January of this year, so a few months, or 1.5 months. But sometimes when it would happen, it would say it's going to take December of next year, close to Christmas next year, which is pretty poo-poo. We can do better than that. So there's obviously GROMACS was misbehaving in this case, so we wanted to sort of figure out what was going on the platform. And when things come up like this is obviously a very serious sign that we need to sort of fix we've got to figure out what the problem is going on, and we need to find some sort of fix to it. So I've been on the job for about 3 months, so I'm still learning from the gurus about what's going on and how to sort of tackle these problems. But sort of what I've got to diagnose the method behind the madness is the RUG method. So it's sort of an acronym that sort of indicates to repeatedly replicate what the problem is, so try to get that bug being replicated so that you can see what's going on. Use profilers, tools, and anything else that you can use to try to diagnose the problem. And really G for grasp and understand what the bug is, so that we don't get it coming up again. We really understand what's going on so it doesn't come up again. Okay, so repeatedly replicating the bug. So what did we do in this case? So what we did was we performed this GROMACS simulation on all of our nodes, which is about, in this case I just looked at the Genoa nodes, which is about 40 of them. And we just ran the GROMACS simulation by itself with nothing else going on the platform. and we tried to see if we can replicate the bug. So what you can see in green is where everything sort of worked out great, so that's all good, ka pai. But in red you can see it's, this is where we're getting problems occurring, and it's a little bit random. So at this point we think, oh, maybe it's sort of a node problem, but we can replicate it, which is important. But what I did next was I said, okay, let's just look at the nodes that didn't work well and just see if we can repeat it again, just to see see if it's a node issue. And unfortunately, this is where we get inconsistencies, where sometimes a node will present itself as not running well, and then it will just go, oh no, I'm happy, I'm fine, what are you talking about, dude? So we sort of get sometimes we get this problem where it's not consistent. But in this case, we're quite lucky that we had 3 nodes at least that were always acting poorly. So we sort of decided to look at those, focus on those nodes to try to figure out what the problem was. And something that I sort of came to realise was from this process, particularly doing this repetition on all the nodes, was how different it is to assess performance on a laptop versus a HPC. Because on a laptop, you've got a single computer, single user, and the processes are pretty controlled. But once you start getting to an HPC cluster, then you're starting to work with multiple nodes which are linked together, so you can have complexity when you've got jobs running across nodes. You've got multiple users using the setup at the same time with multiple jobs running concurrently. And that's in particular why we made sure that we, when we were looking at one node only when diagnosing the problem, and only allowing one user so myself in this case, to use the node. So then second, we use profilers, tools and logs for debugging. So there's a whole range of profilers and tools that we can use, so I'm not going to go through lots of them. I just thought to highlight this one in particular, which is vTune. vTune is really handy because it sort of gives you a look under the hood about what's going on when your algorithm's running. So in this case, there's 2 panels to particularly look at. This top one, which is called a flame graph, indicates what the processes that are running by the program. And the bottom one is your what's happening with the CPU. So it's a little bit like Task Manager on Windows, but it's very tuned for what the algorithm that you're looking at is. And what was really useful to see was looking at how these flame graphs and the CPUs were acting differently between a behaving job and a poorly behaving job. Specifically, when looking at the flame graphs, you can see this black box. That black box is indicating that's the program is running. And what you could see when it was misbehaving was it was doing not that many of these black boxes, but more of these red boxes. And this was actually just MPI waiting. So the program was just waiting for things to happen. And you can sort of see that down below where if you look at the CPUs, the sort of on the behaving side, they're running at 100%, all fine. But then when we look at the misbehaving one, we can sort of see there's times where it's running at full capacity and then it's not. So there was definitely something weird going on. So I won't go too much into what was actually happening behind things and all the things that we did, but one of the profilers that we used was HTOP. And this is, again, another one of these like task manager types of things that indicates what jobs are running on the nodes at any one time. And so what we found was that when I was running my job, HTOP was indicating that, yeah, my process was running, that was all hunky-dory, but it was also saying that some other processes were running from other jobs. And this is really weird because I had asked the computer to only let me on and nothing else. And so this was quite suspicious. So I brought this up with our team to bring this up as an issue. And we sort of, and in particular, I brought it to one of our gurus, Peter Maxwell, that some of you may know. And he sort of took a little bit more of an interest in this, or took a little bit more of a look inside of what was going on. And he found that these jobs were actually zombie jobs. They were essentially just running in the background, not doing anything, but using up CPU time, which is probably a little bit why the CPU here was going up and down, because sometimes it was doing GROMAC simulations, sometimes it was doing vast nonsense. So the solution to this was actually quite simple: clear the jobs And once we did that, everything was running hunky-dory and particularly fine. And to date, we haven't seen any other problems occurring so far. We are getting zombie jobs popping up, but we're able to see them and clear them as they go. And we're hoping that a few updates on our HPC will soon sort those out full stop. So my colleague sort of told me, was thinking about this from a monetary point of view, and he was, once he calculated up, I don't know how he got to this number, I think it's extreme, but he said the potential saving over a year if we had lots of these jobs running, well, to put it back in perspective, what we find is when we see performance issues like this, they're coming up because a user has said, you know, this is happening. But in many cases, users will run the platform and think, oh, I'm doing a simulation, it's going to take this long, oh, that's the price of doing business. So sometimes we'll see that some of these jobs, like, and not particular, in particular, Greymax was running slowly in this case, but we also found that other jobs were running slowly, especially if they're running MPI processes, that they're running slowly as well, which were cleared once we got rid of these zombie jobs. So overall, if we take everything together, we're looking at significant cost savings in terms of computing. And in particular for us, we're looking at really much better efficiencies. So in conclusion, I hope I've just highlighted that when we're looking at large research-based computer clusters, they're complex beasts, and they sometimes work in really bizarre ways. Sometimes problems can come up that it's quite subtle and debugging can be quite hard to do. But using this RUG method, we can help diagnose what's sort of going on. And just to emphasize again that if you have any problems at all, no matter how big or small they are, because in this case, this was a case where the supervisor came to us because they just thought, oh, this is really bizarre, but I think, I'm sure that something's going on. They still didn't get in contact with us for a while until they sort of confirmed what was going on. So it's good to do that, but any problem, big or small, or any suggestion that you've got about making our products, I guess, in a sense, better. We'd love to hear from any one of you, from everybody. So I will thank everybody on my team, particularly Peter, Alex, and Chris, and thank you for listening. And hopefully it was short enough because I know, you know, the last person before lunch, everybody's eager.
You were well on time.
Cool.
Thank you very much, Geoffrey. Other questions for Geoffrey?
Hi, do you keep a knowledge base of all these issues you solved and
Yes, we do. We will put something into our Jira database to log what's gone on, as well as a Confluence page, which is a little bit like a wiki page. So we sort of keep that up to date with any of the problems that come up, such as this.
I'm curious to understand more about where these zombie jobs come from. Is it something that just happens in the system, or is it people doing things, external users doing
In this case, the zombie jobs came up because there were particular jobs that people were either timing out or people cancelled. And what should happen by the scheduler is that it should just cancel everything. Mm-hmm. But sometimes it seems like maybe that's not always happening. Mm-hmm. And also, particularly the program VASP is a bit stupid. It doesn't know when to die. So sometimes if it goes on, it sometimes goes on a path on itself and so it doesn't find its way back to the track. So sometimes it's a software thing.
Okay.
Yeah.
Yeah. Another question? I had one other question. Naive. Is the RUG method something that's widely known about? And
no, I just made it up for the talk, just because I wanted something that was easy to remember.
Yeah, and I guess if you
and my colleague said, oh, it's nice because you're pulling the rug from under the bug.
Yeah, so, you didn't tell us that.
No, so that's the way to remember it.
Yeah. Great. That'll end up on the Confluence.
Yes. Yeah.
Cool.
Oh, Maxine.
Yeah, amazing systematic investigation, by the way. How much time did it take you from finding
Yeah, so I was actually lucky because when they came to us, it was just before Christmas. So I just put all the longest thing is just to get a node by yourself, because obviously everybody wants to use it, and getting a whole node is, you know, you're taking away a lot, you know, resources from everybody. So I only ran 10-minute jobs, guys. So I didn't take away lots of time from the users. But yeah, so I actually just ran it over Christmas. So by January when I got back, I was like, oh yeah, there's definitely something a bit funny going on. So if you bring the bug to us at a convenient time, then it's fine. Then it doesn't take too long. But we'll investigate it any way that we can. So always bring your bugs to us. Yeah.
Are your diagnostic tools available for everybody, or is it more like?
I'm not too. Oh, yeah, so if you are using, if you're on the REANNZ platform, yes. So things like VTune are available. Yeah. I don't know if they are freely available for everybody, you know, outside of the platform. I think VTune in particular is, but I'm not too sure.
Good. Thank you, Geoffrey, and thank you everyone for your talks today. We're going to head into lunch now.